Okay, hi. So here's part two of the video of trying to prove various functional properties using formal definitions. So we're going to be proving that this function is surjective. You may notice that it is a little bit different than the function that we proved was injective in the previous video. Unfortunately, so this is the way it looked in the previous video. When we proved this function was injective. Unfortunately, that's a slight mistake. So, oops on my part. It should be that this function actually fails surjectivity for exactly 1 point. There's 1 point that doesn't get mapped to. Hopefully, you'll see it from the next example. We'll talk about it then. But for the purpose, this function is very, very similar. And if you look at, if you go back to the proof of injectivity, the fact that whether or not those parentheses are there actually makes no difference at all. The proof will go the exact same way. So I'm just going to consider for future just ease of speaking. I'm going to say that we prove this function is injective because again the proofs are very, very close. But I apologize for this. This is the particular function I want to prove is surjective. So the idea, our plan here is that we want to say for every element y in the codomain, we want to find an appropriate alpha where f of alpha equals this y. If you remember for the proof of injectivity we had to break it into several cases. For that, we said there were two elements s and t in the domain, and we wanted to prove that if their outputs were equal, if the corresponding outputs that the function sent them to were equal, then that needed to mean that s and t were in fact the same element. So we ended up with a case-by-case proof because we didn't know anything about these two elements, so we just had to break it down into cases, saying, okay, well, if our function treats them differently depending on if they're even or odd, we need to know whether or not these s and t are odd. Because they're arbitrary, let's just look at all the cases. Let's look at when they're both even. Let's look at when they're both odd. Let's look at when they have opposite parity. For this case, though, or for the proof of surjectivity, we do want to we do want to break it down into cases, but it's not going to be based on what the inputs are because we're allowed to just say what the input is. The difference is it needs to be based on what y is. And because this is a piecewise function, it might not be clear about different cases we need to consider. So you don't need to graph it, but it might actually help to just kind of consider what this function is going to look like graphically. So we've got the natural numbers here on the x-axis. Those are going to be our inputs, and our outputs are going to be integers. So we can just start thinking, what's f of 1? F of 1, well, 1's an odd number, so negative 1 plus 1, that should give us 0. When we have 2, 2's an even number, so we'll get 1. F of 3, negative 3 plus 1 all over 2 should give us negative 1. F of 4 divided by 2 gives us 2. And then hopefully you can see a pattern here. This will be negative 2. And then going on and on like this. Notice that for all of these points up here, for all of these points here, that's 2, 4, 6, 8. Those are the even. Our input's even. And for all these down here, our input is odd. So because we don't know what this y is, we want to break it down into cases depending on what that value of y is, and then we can just say directly what the corresponding alpha is. So what's the difference between these two? Focusing on y, focusing on the output. Well, it seems like a good way to look at it is the first case should be when y is 1 or greater. I'll just say y is greater than 0. And then our goal is just to find an appropriate alpha. And then the second case is y is not greater than 0, so we'll say it's less than or equal to 0. And again, the same thing is we want to find an alpha in both those cases, so that f of a equals y, such that f of a equals y. So that's our goal. Not obvious at first, but in order to break it down into different cases, that will allow us to be a lot more precise. So we're not actually proving anything yet. We're just kind of sketching out how this proof is going to look. Second of all, let's go ahead and find out what these alphas need to be in these cases. So if we do that, it's going to make our proof a lot clearer, because we just say case 1, let y be greater than 0. Let's figure out what alpha needs to be, and then just say for this alpha it will give us the y. Case 2, y is less than or equal to 0. Pick this alpha, and it's y. So let's actually look at those two cases and figure out if we can pick alpha. So if we have case 1, y is greater than or equal to 0. Let's try to find alpha. So you'll notice it's kind of weird like this, like what case are we supposed to use? So looking at our graph here, you can see, looking at our graph here, you should see if y is greater than 0, we will have an even input. So that actually does kind of help us. We want y to equal f of a, or f of alpha, and we want that to be alpha over 2. So that would mean that 2y equals alpha. When we did this, we just kind of said, let's hope that alpha is going to go into this function correctly. But when we do this, this actually tells us two things, which are both very going to be important. So if you remember going back to example 1, we had that fake proof that a function was surjective. The idea was that particular input wasn't actually part of the domain. So our proof of surjectivity failed. But here, since y is greater than or equal to 0, or sorry, it should be that y is strictly greater than 0. Thank you. So since y is greater than 0, that means 2y is also going to be greater than 0. So because 2y is going to be an integer that's greater than 0, that means alpha equals 2y is in fact an element of the domain. So that's good. So there is an element of the domain that will actually map to y. But more importantly, or just as importantly, is it actually going to be an even number? I mean, yeah, right? So it has the exact form of an even number. If it's 2 times some integer, 2 times some integer means that alpha will be an even number. So we know plugging into the function will actually work as intended. So I'm going to go ahead and organize our thoughts kind of here on the final slide. If y is greater than 0, pick alpha equals 2y. Next, if y is less than or equal to 0, pick alpha equals, and then we just need to find the appropriate value of alpha. So looking at this next case here, case 2, let's take y less than or equal to 0, and our goal is to find alpha. So we would want y to equal f of alpha. And again, we don't really know. It's a lot less clear in this case, but we know from our previous graph that we want alpha to be an odd number. So let's just assume it's an odd number. Again, this is just scratch work, so we're just allowed to play around with what's convenient for us. But let's assume that it's going to work out where alpha is an odd number. And let's pick let's pick that second branch to use. So we have y equals negative alpha plus 1 over 2. That would mean 2y equals negative alpha plus 1. That would mean 2y minus 1 equals negative alpha. So alpha equals negative 2y plus 1. So there's two things we need to check. First of all, is this an odd number? That's probably easier to do, right? Alpha is odd since alpha equals negative 2 times y. We could think about that as 2 times negative y plus 1. So that's the exact definitional form of an odd number, with negative y being an integer. And the second thing we need to say is we need to show that alpha is in fact part of the domain. Which that might be a little bit harder to do, because there is like a negative number here. We don't know exactly what y is, except that it's less than 0. But I mean, that is actually pretty convincing, right? Since y is less than or equal to 0, negative 2y is going to be greater than or equal to 0, right? So it's going to be a negative number times a negative number, or 0 times a negative number. And that would mean negative 2y plus 1 is going to be greater than or equal to 1, because that's alpha. Alpha is an integer, or whatever. It's a number. Okay. Alpha is going to be an integer, because it's an integer times an integer plus an integer. So it's going to be an integer greater than or equal to 1, so it will be a natural number as well. So these two things are pretty important to check. Again, that's why example 1 failed. We were able to push symbols through and get something that ended up looking surjective when it really wasn't. And the reason why is because we need to make sure that these inputs that we pick are actually valid. They actually go in the function the correct way. And finally, that they're part of the domain that they're supposed to be in, that we're not trying to consider inputs that are actually outside of the domain. Okay, so if y, this is kind of just the summary of our scratch work here. If y is less than or equal to 0, we want to pick alpha equals negative 2y plus 1. So that's kind of our scratch work. But now, with that out of the way, our final proof is actually going to be very, very clean. So let's actually prove this now. We're ready to do the final formal proof. So proof: take an arbitrary element of the codomain, and we want to show that for this choice of y, there exists an element alpha of the domain, such that f maps it to this y that we picked. So we figured out what our two cases need to be. Case 1, suppose y is greater than 0. Then pick alpha equals 2 times y. Which is note that alpha is going to be an element of the natural numbers because y is greater than 0, and we're just multiplying it by another positive number. So greater than 0 integer multiplied by a positive number means that it should be in our domain that we want. It should be in the natural numbers. Moreover, alpha is even because it's 2 times an integer. So there's the factor of 2. Therefore, f of alpha, and all that's left in this part is we just say, okay, well, when I plug it in, I do get the value of y that I want. So because it's even, we're allowed to use this first case, or we have to use this first case. So we've got alpha divided by 2. Of course, that equals, because alpha equals 2y, it's 2y divided by 2 equals y as desired. Maybe we can say, just to be clear, that we're taking a step away from case 1. Now suppose y is less than or equal to 0. So these are our two cases that we have. First one, we just to summarize for the first one, we said, okay, well, suppose what makes it special about this first case. Let's take the case that y is, or that our output's going to be a positive number, and then we say, okay, well, this exact alpha that we picked, not only is it part of the domain, but it's an even number, so we know how to map it using this f to get exactly y as required. So now suppose y is less than or equal to 0. Then pick alpha equals negative 2y plus 1. And although we did the work on the previous page, I think it's probably, because this is one of the trickier parts of the proof, it's probably good to go over that again in the final proof. So you can say, note that alpha is in fact part of the domain, since y greater than, or sorry, y less than or equal to 0 implies negative 2y is going to be greater than or equal to 0, which implies negative 2y plus 1 is going to be greater than or equal to 1. And then you can say, furthermore, alpha is odd because it's of the form 2 times an integer plus 1, 2 times an integer negative y plus 1. Furthermore, it's odd, so now all that's left to do is plug f of alpha, or plug alpha into f, and we get negative alpha plus 1 divided by 2. Be careful here. Classic algebra pitfall. Make sure that we're going to distribute this negative sign, that we're taking the negative of the entire value of alpha. Equals, and then that is going to be 2y minus 1 plus 1 all over 2, so that's going to equal 2y over 2 equals y as desired. So that's actually the end of the proof then. For either case that we're in, these are the only two, or this is a clear divide of all the possible cases that y could be. Either it's going to be greater than 0 or it's not. And in this case, we're able to pick an alpha that will reliably be in the domain and map to this value of y. In the second case, we're able to pick an alpha that is definitely in the domain, and it will reliably map to this value of y. Because our choice of y was arbitrary, we're always able to find an alpha that maps there, and therefore, I'm kind of out of space here, so that's annoying actually. Here, I'm going to move this up here, and then get rid of that. Get rid of that little tiny line. Just because I want to emphasize the end of the proof. So let's say I do think ending proofs and kind of being clear about the logical steps at the end of the proof is pretty important. Okay. So here's an example of a way to end the proof. Again, just to summarize, so you don't make the reader pick up the pieces and understand the implications. Since our choice of y was arbitrary, and our cases cover all possible values of y, we can always find an alpha in the domain such that f will map that alpha to y. So f is a surjection. And that's it. So I do want to reiterate one more time, the fact that we were able to do the fact that we were able to do kind of the groundwork beforehand of figuring out exactly how our proof is going to look and what our choices of alpha were going to be. It's going to be very, very helpful in longer proofs. It's going to be very helpful in longer proofs to kind of do that legwork beforehand, so it's a lot clearer. If you're trying to, in the middle of the proof, figure out what your alpha is and you keep that work in, it really muddies the waters of what depends on what. So if you just say, okay, start with this y, now pick this specific alpha, and then show that it works, that's so much more effective proof. It's much clearer, and I think that you'll be a stronger proof writer for it.